Okay, so we have talked about fluid statics, wherein your fluids are not moving, and we tried to compute pressure variations depending on the height or elevation of the fluid. Okay, now let's get back to when your fluid is in motion. Okay, so gumagalaw, nagmo-move, and we need some way to characterize the motion or the flow of your fluid. We need to know when does it become a laminar flow, or what we know as streamline flow, or when does it become a turbulent flow. Okay, so you can see the difference between laminar and turbulent flow here. As you can see, in laminar flow, the flow pattern like this is smooth. Okay, the layers of fluids just slide past one another. And it's known that this regime exists at low velocities. While in your turbulent flow, it exists with higher velocities. And as you can see, it's characterized by the presence of swirls, or we know them as eddies. Okay, and the flow pattern is unstable. So whether the flow is laminar or turbulent depends on some factors, such as the geometry. Like, for example, is the flow inside a certain geometry or tube or shape, or is it flowing past this object? Okay, it also depends on the size, all right, or dimension of that particular geometry. It could depend on fluid properties as well. The reason why we need to know or determine yung flow regime is because turbulence can either be an advantage or a disadvantage. It's an advantage in chemical processing because it allows a more efficient mixing of your fluids. Okay. In terms of, let's say, if you want to cool down some materials or let's say food, okay, mas maganda, mas advantageous din ang turbulence because magiging mas efficient at mas mabilis kapag kinu-cool down mo ang isang material or food, right? When you try to blow it down. While it could also be a disadvantage, okay? For example, airflow around a vehicle, all right? Kapag mataas yung turbulence, mataas yung resistance. So ang ginagawa ng mga automobile manufacturer is that they try to suppress the turbulence, okay, by designing the car to lessen the resistance, to lessen the turbulence, and thus improve efficiency. Isa pang bagay kapag sa automobiles, okay, or other vehicles is yung noise. Okay, so turbulence could cause some noises. Okay. Also in biology or medicine, turbulence is known to be of disadvantage. Okay, especially if you put in some medical device or let's say catheters or coronary stents, okay, in your blood vessel. So what will happen is that magkukos siya ng turbulence, okay, like that. And that will result to increase in perfusion pressure, okay? So let's say you have here a curve that characterizes that. So blood flow is known to be laminar. And the reason it's laminar is it's because of the very small size of your blood vessel. Okay. However, if you put in there a medical device or a stent, for example, it might cause some turbulence because the fluid will now flow past that device or object. At kapag nangyari yan, the regime, okay, will deviate from that black curve here, magiging red na siya dito, like that. Okay. So with the given flow, for example, kapag laminar siya, okay, you will need a certain perfusion pressure or blood pressure, right? Pero kapag may turbulence, okay, that perfusion pressure will increase. Okay? So yung systolic and diastolic pressure mo, tataas yun. All right. So we want to characterize the flow regime. So the question is how? So turbulence or laminar, okay, depende yan perhaps sa geometry or size ng kung saan may flow. Again, whether the flow is inside the object or past the object. Okay. So it could, size could be a factor, geometry could be a factor. Will it change if instead of a circular cross-section ng pipe, magiging square siya or some other geometry? So we want to know that. Maybe it's also a function of fluid velocity, right? Kasi malamang mas mabilis yung fluid, yung flow, okay? Yung mga molecules doon sa fluid mas nakakaandar sila, okay? They can move with more freedom, right? Also because of the increase in size of the pipe, for example, mas marami silang, mas malaki yung kanilang freedom to move around, okay? Maybe density is also a factor. Okay, perhaps fluids with higher density tend to not move too much. Okay, and even viscosity, right? Maybe yung mga mas viscous na fluids. Again, since viscosity is your resistance to flow. Okay, so the greater the viscosity, the greater the tendency to resist flow, and that might result to the fluid flow being laminar instead of turbulent. Okay, so how do we do that? So the way we can examine that is through by doing some experiment that will allow us to change some of these factors. So let's say I have here a reservoir of water, and this water flow is what we would like to characterize. Okay. Now, in order for us to visualize this flow, we need a tracker like a dye. Okay. Now, this water flows through a tube like that. Okay. And we want to know whether by changing some factors, what will be the effect to the flow regime. Okay. So, the geometry, of course, we want to hold that as constant. All right. There's no way we can vary the diameter of this pipe here. All right. See fluid density, since we are using water, okay, isang fluid lang ang gusto nating i-examine. So there's no way for us to change the density as well. Well, maybe except if we can vary the temperature, but in this case, let's hold the density constant. Okay, what else? See viscosity. It's the same with density. You can hold that as constant kasi water lang naman yan. All right? Again, maybe by varying the temperature, you can change the viscosity. But the genius about this setup is that we can perhaps just vary one factor, which, of course, the easiest one to vary is your fluid velocity. Right? So all we have to do is to perhaps try to vary the opening here, or the amount of fluid that can be allowed by the valve to pass through. All right. So in doing so, It turns out that there is, if you hold the size, let's say the diameter, density, and viscosity as constant, mayroong velocity kung saan siya ay pwede nating tawaging critical point. So yung velocity na yon, if it exceeds that critical point, the flow will be turbulent. If it is below that critical point, the fluid flow will be laminar. Okay, so it turns out that it's an interplay between the inertial forces in the fluid and the viscous forces in the fluid. So anong ibig sabihin no? Yung fluid meron siyang inertial force, and this inertial force can be a factor or can be a function of your diameter, your velocity, and even your density. Kasi mas, pag sinabing inertial force, gusto ng fluid gumalaw, okay, the greater the inertia, the more na mahihirapan tayong pigilang mag-flow yung fluid. Okay? And the factors that could affect that would be your diameter of the pipe, yung velocity niya, of course, kasi mas mataas yung velocity, mas sumagalaw pa siya. And then maybe the density, right? Okay. On the other hand, pinipigilan naman nito ng viscous force. And of course, it's in the form of your viscosity. Okay. So the greater the viscosity, the tendency is that the fluid will not flow too much. So it's an interplay between these two forces. Okay. So if the inertial forces, okay, are higher, magiging turbulent yung flow natin. While if the viscous forces are higher, okay, medyo tatamad-tamad gumalaw yung fluid, so perhaps it becomes laminar. Since we performed that experiment a while ago, and we can know if we hold d, rho, and mu as constant and varying the velocity of the fluid, okay, and if we take that ratio between inertial forces and viscous forces, we arrive at a dimensionless number which we call Reynold's number. Okay, so since we know that velocity kung saan you will arrive at the critical point, and that critical point turns out na ang value niya ay 2100 to 4000. That's practically the transition period. So less than 2100, the flow will be laminar. And if the Reynold's number is greater than 4000, the flow will be turbulent. Okay. Now this criteria here is only true for tubes, okay, or pipes or geometries with circular cross-section. Okay. If the cross-section is non-circular, you have to compute for what we know as the equivalent diameter, okay, which is basically 4 times the cross-sectional area of that geometry divided by its wetted perimeter. Wetted perimeter means kung ano yung side ng cross-section ang naaabot ng fluid. Okay, now let's talk about laminar flow in your pipes. Okay, and in some other lecture we can talk about turbulent flow. Okay, if you have a pipe like that, okay, and let's assume that it's a circular pipe, and if you allow laminar flow to occur inside that pipe, we can determine the velocity profile or velocity distribution. So what do we mean by this? Number one, let's say that we characterize this flow in one dimension only. So ibig sabihin, the flow is going on, okay, from this point to the right. Okay, pero ang tanong, yung variation sa velocity, saan siya nagva-vary? Yes, the flow is going from left to right, pero yung velocity niya nagva-vary din ba from left to right, top down, or in the or in the third dimension, let's say the or in the y dimension perhaps. Okay, so let's have first, we can assume na 1D lang yung flow and yung variation. So ibig sabihin, velocity, which is characterized by these arrows here, varies only dito sa vertical direction, which we say here as the r direction or the radial direction, because it's a circular pipe, right? Ibig sabihin radius to. So the velocity changes with respect to the radius. Okay, so if we have a 1D motion and if the flow is laminar, okay, and if the flow is steady, it turns out that the velocity profile will look like this. Okay, where the maximum velocity occurs at the center. All right. So the velocity distribution in equation form looks like this. Okay. So it's a function of your radius. Okay. So if you change the radius, what will happen? What will happen to the velocity? And of course, there's your delta p. Because let's say that this flow here is pressure driven. So there's a pressure difference between these 2 points, left and right. Okay, and it also depends on the viscosity and the length. Okay. Now, from this velocity profile, you can derive your volumetric flow rate. Again, you can only use this formula if the flow is laminar, steady, and 1D. And if it's a pressure-driven flow. Okay? So we call this the Hagen-Poiseuille equation. And if you notice, this equation gives you the volumetric flow rate if you know radius or pressure drop or pressure difference, right? So your flow rate strongly depends on the radius kasi naka-raised to 4 siya. In other words, if you change the radius, it will dramatically affect the value of your flow rate. All right? So you notice, no? Proportional CQ, flow rate kay R to the 4th power. How about delta P and R? So inversely proportional sila, right? In other words, if you have a given, let's say, pressure difference, you will be able to determine the radius. If you change that, okay, you will notice the change in R and noticeable siya kasi naka-raise to 4 nga siya. Okay. So, for example, an application in the field of medicine. So let's suppose that the flow rate of blood in a coronary artery has been reduced to half its normal value by plaque deposits. Okay. So sa kakakain mo ng mga cholesterol na pagkain, crispy pata, sisig, lechon, yan ang nangyayari. Okay. Ang tanong, by what factor, okay, has the radius of the artery been reduced? From the original radius, ano na siya ngayon? Yung size nito. If we know that the flow rate has been reduced to half. Okay? So, how do we solve that? We will use the Hagen-Poiseuille equation, and the form is like this. And we know from this equation, if we hold the others constant, like your delta P, your viscosity, the length of the blood vessel, for example, we know that the relationship of Q and R is like this. Q is proportional to R raised to 4. Such that from this proportionality relation, we know, therefore, na Q nu over Q old equals R nu over R old raised to 4. Okay. Now, sabi sa problem, yung bagong flow rate ay na-reduce into half na lang, right? So that's 1/2 times Q old. Okay. So to get R nu over R old without the exponent, so it will be like this. and you can cancel out Q old like that. Therefore, you will end up with 1/2 raised to 1/4. Okay, and that is equal, okay, to 0.841. Or in other words, the new radius will be 0.841 times the old radius. So it's around 16% decrease in the radius. Okay, so it's a very useful equation, not just in medicine, but also in other applications in chemical engineering and mechanical engineering. Okay. So let's say if you change R, like what happened here, okay, depends on how much you change R. Halimbawa, you increase the radius because of some vasodilators, or if you decrease it because of some vasoconstrictors, there will be an effect to delta P. And the effect will be great, right? So delta P here can be your blood pressure or your perfusion pressure.